Having established the rules and the laws for limits in the first video here for 2.3, we're going to spend this video just looking at some examples that you may find useful for your homework. Let's start with number 1, where we're given some information. We're told that we have a function f, and the limit as x approaches a of that function f is equal to -3 for some value of a. We're also told that for a function g, the limit as x approaches that same value of a of g of x is equal to 0. And finally, the limit as x approaches a of h of x for that same value of a is equal to 8. We want to find then some values of some particular limits. Let's start with part A. We want to find the limit as x approaches a of the function f of x plus h of x. Well, we are told in rule 1 of this section that the limit of the sum is the sum of the limits. So this is going to be the limit as x approaches a of f of x plus the limit as x approaches a of h of x. And we're given what those are. Limit of x approaches a of f of x is -3. Limit as x approaches a of h of x is +8, so we get a +5. Let's look at a couple more of these maybe. How about, I don't know. How about part E? We want the limit as x approaches a of f of x divided by h of x. Well, according to our limit laws, the limit of the quotient is the quotient of the limit, so we can take the limit as x approaches a of f of x and divide that by the limit as x approaches a of h of x. Now, the limit as x approaches a of f of x is -3. The limit as x approaches a of h of x is +8, and so we get -3/8. Remember, the only thing we'd have to worry about here is if the denominator limit is 0, then the overall limit would be undefined, but that's not the case here. So I think we get the idea of using those basic limit laws as seen in number 1. Next problem we want to take a look at is number 4. We're asked to evaluate the limit and justify each step indicating the appropriate limit laws. So what we're looking at is the limit as t approaches -1 of the quantity t squared plus 1 to the third power times t plus 3 to the fifth power. So now to evaluate this, what we're going to do is first we're going to look at some limit laws as defined in our book. So the first one we can do is say that the limit of the product is the product of the limits, which is number 4. So this is by law number 4, which says that the limit as t approaches -1 of t squared plus 1 to the third times the limit as t approaches -1 of t plus 3 to the fifth. Now the next law that we can use is the power law, and that's number 6. By law number 6, it says the limit of a function to a power is the power of the limit of the function. In other words, we can take the limit as t approaches -1 of t squared plus 1 and then take all that to the third power. In the same way we can do that for the second function, take the limit as t approaches -1 of t plus 3 and then take all that to the fifth power. Okay, now by limit law 1, we can split up this addition here inside the parentheses. We have the limit as t approaches -1 of t squared plus the limit as t approaches -1 of 1, and then all that's going to be raised to the third power, times the limit as t approaches -1 of t plus the limit as t approaches -1 of 3, all that raised to the fifth power. So here we're using the first law that says that the limit of the sums is the same as the sum of the limits. And then finally, I think we can, by rule 7 and also rule 9. Rule 7 says that the limit of a constant is just going to be that constant. And rule 9 says that the limit of a power function is going to be just the value evaluated at that power function. So, in other words, by rule 9, we have the limit as t approaches -1. Actually, we can just put that in here. It's going to be -1 squared plus the limit as t approaches -1 by rule 7. That's just going to be 1. And that's all to the third power times the limit as t approaches -1. Well, this is the power rule where n is equal to 1, so we can just replace t with -1 here, plus the constant rule number 7 says the limit of a constant as t approaches a value a is just going to be that constant. So we'll have all that to the 5th power. And now just evaluating these here, we have negative 1 squared, that's 1 plus 1, that's 2 cubed, times negative 1 plus 3, that's 2 to the 5th. And so let's see, 2 to the 3rd is 8, 2 to the 5th is 32. We get a final answer then of 256. So just familiarizing yourself with those limit laws, that's a good problem to do right there. A couple other examples that we want to look at. Let's take a look at number 10, where we see that the limit as x approaches, we want to find the limit as x approaches negative 4 of this rational function, x squared plus 5x plus 4 divided by x squared plus 3x minus 4. Now, remember we did have a limit law that said we can just plug the number in for a rational function as long as that number is in the domain of the rational function. But notice here that if we factor the denominator, which I think we can do, we get x, let's see, what are we going to get? X plus 4 times x minus 1. And that means that negative 4 is not in the domain of this function. In fact, if we plug negative 4 into our function, it is undefined. So we can't just plug negative 4 into the function and get the limit that way. We're going to have to do something different. We could factor the denominator. Maybe we can also factor the numerator. I think we can, into x plus 1 and x plus 4. Well, notice what happens here then. We can simplify the original function by dividing the x plus 4 factors down to 1. And so, since the function has the same value everywhere except x equals negative 4, this new function that I got after canceling the x plus 4 factors is going to have the exact same values as the original function except for at our a value of negative 4. Well, that tells us then by the law on page 111 in the box, about 3/4 of the way down, that if the two functions equal each other, as long as the x value does not equal a, then the limit as x approaches a of the two functions will be the same. And so now we can use the fact that this is a rational function where negative 4 is in the domain, and that means we can just plug in negative 4. It's going to be negative 4 plus 1 over negative 4 minus 1. Negative 4 plus 1 is negative 3 over negative 5, or positive 3/5. So positive 3/5 is the limit of that function. And we did that again by factoring, canceling, and using the fact then that the two functions agree everywhere except for a when x is equal to negative 4. The original is undefined there. But now we got to the point where we had a rational function that is defined at negative 4, has negative 4 in its domain, so we could just plug it in and get the limit. How about number 15, where we're looking at the limit as h approaches 0 of the quantity of 4 plus h squared minus 16, all divided by h. Obviously, this is a rational function that is not defined at our value of a, which in this case is 0. And so we can't just plug 0 into our function because the function is undefined. What we're going to try and do is find an equivalent algebraic function that agrees with this function everywhere except perhaps h equals 0, and then try and find the limit that way. So what we're going to do is we're going to maybe do a little bit of algebra here. So this is going to equal the limit as h approaches 0. Let's square out this 4 plus h. So we'll have 4 plus h times 4 plus h minus 16, all divided by h. This then is equal to the limit. As you're writing this out, make sure that you're rewriting the limit every time. That's the appropriate format. And make sure that you do write this stuff out. Don't just watch it and then try and guess on your homework. The way to learn math is to write math. So you should be writing these problems out, trying some on your own, writing them out, trying to use the correct notation. That's the best way to learn mathematics. Alright, notice what happens here. We got a positive 16 and a negative 16 in our numerator. Those go away, and so we're left with then the limit as h approaches 0 of what? 8h plus h squared divided by h. Well, hey, that means we have the limit as h approaches 0. We can factor an h out of the numerator, and we're left with h times the quantity of 8 plus h over h. Here the h's divide to 1, and so this is going to equal then the limit as h approaches 0 of just 8 plus h. And now we have a polynomial function that is defined at h equals 0. So we can just plug that in, the 0 in for h, and we get 8 plus 0, or just 8. So you get the idea. A lot of these functions where you start off with a rational function that is undefined at the value that you're trying to take the limit at, what you can do is just do some algebraic manipulation, simplify it, and hopefully you get to an equivalent form of a function that is the same everywhere except for a, and you can take the limit of that. Actually, the next problem I want to do is, let's take a look at number 20. We have the limit as h approaches 0 of the quantity of 3 plus h to the negative 1 minus 3 to the negative 1, all divided by h. Again, our function here is undefined at our value of a, the point that we're approaching with our limit. And that's okay because we actually don't consider that value when we take a limit, but we're going to want to try and find an equivalent form of this function that we can find the limit. Because we can't just plug 0 in for h here if the function is undefined when h is equal to 0. So let's go ahead and see what we can do here. Remember, we take the limit as h approaches 0. Always rewrite that notation every step of the way. Quantity to the negative 1 power is the same as 1 over that quantity. So minus 1 over 3 all over h. Well, we need to get a common denominator here, so I can multiply the first one by 3 over 3, and the second one by 3 plus h over 3 plus h. So we're just going to try and combine those two fractions in the numerator. What does that give us? Well, that's going to give us the limit as h approaches 0 of 3 over 3 plus h minus the quantity of 3 plus h over, let's see, this is going to be a 3 times 3 plus h is our common denominator. All of that over h. So we have then the limit as h approaches 0 of combining those two fractions now that they have a common denominator, 3 minus the quantity of 3 plus h, all divided by 3 times the quantity of 3 plus h. All of that then divided by h. Well, distributing that negative through there, you can see that we're going to have a 3 and a negative 3 cancel, and that negative is going to distribute to the h. So we're going to be left with then the limit as h approaches 0 of a negative h over 3 times the quantity of 3 plus h, all of that divided by h. Or all of that divided by h over 1. We have a fraction divided by a fraction here, so we can multiply the first fraction by the reciprocal of the second fraction. This is negative h over 3 times the quantity 3 plus h times 1 over h. And now these h's divide to 1. And so we're left with then the limit as h approaches 0 of negative 1 over 3 times the quantity of 3 plus h. Hey, we can take that limit now because this is a rational function which is defined, which has 0 in its domain. And so this agrees with the original function everywhere except for at h equals 0. So by our limit laws, we can say that this then is equal to negative 1 over 3 times the quantity of 3 plus 0, or negative 1/9, and that's the limit of that function. So we did some algebraic manipulation to get a function that is equivalent to the original everywhere except for our a value of 0, and then took the limit at that point, and that is the limit of the original function, negative 1/9. I want to say a couple of words about number 28. We're going to be using the squeeze theorem here, that it says that if 2x is less than or equal to some function g of x, which is less than or equal to x to the 4th minus x squared plus 2, we want to evaluate the limit as x approaches 1 of g of x. Well, by the squeeze theorem, the limit as x approaches 1 of g of x will be less than or equal to the limit as x approaches 1 of x to the 4th minus x squared plus 2, and it'll be bigger than or equal to the limit as x approaches 1 of 2x. Since 2x and x to the 4th minus x squared plus 2 are polynomial functions that are defined at 1, well, you can just go ahead and take the limits of the right side and the left side of this compound inequality by plugging 1 in. And what you see then is that you get 2 is less than or equal to the limit as x approaches 1 of g of x is less than or equal to, let's see, 1 minus 1 plus 2 is also 2. And so since this limit is bound between, well, this function approaching 2 and this function approaching 2, the limit as x approaches 1 of g of x also must be 2. So I guess I did more than say a couple of words about it. I guess I actually solved the problem. Last one I want to look at then is number 32 out of your book, where we're asked to find the limit if it exists. Looking at the limit as x approaches negative 6 of 2x plus 12 divided by the absolute value of x plus 6. Well, remember that by our limit laws, this is going to be equal to the limit as x approaches negative 6 of the numerator divided by the limit as x approaches negative 6 of the denominator, provided that those limits exist and are not and the denominator 1 at least is not equal to 0. Well, the numerator 1 is going to exist. The numerator 1 is just a polynomial, and then we can just plug in negative 6 here, and we get 2 times negative 6. That's 0. Now the question is, what about this limit here in the denominator? The limit as x approaches negative 6 of the absolute value of x plus 6. Well, remember what the absolute value function is. It's really a piecewise function. And if we have the absolute value of x plus 6, that's just the original absolute value function moved over 6 units. 4, 5, 6. So here's negative 6. And here's the absolute value of x plus 6, that function. So this is y equals the absolute value of x plus 6. Now the limit of this thing as x approaches negative 6. Well, does it exist? Well, it does look like the limit agrees. As we come in it from the left, the function value approaches 0. As we come at negative 6 from the right, the function value approaches 0. So it does look like the limit as x approaches negative 6 of the absolute value of x plus 6 is equal to 0. But now that's a problem because we can't use our limit law if for the quotient of two functions if the denominator function has a limit that's equal to 0. So let's take a look at this function a little bit more closely. Let's look at the function y equals the absolute value of x plus 6. What is that equal to? Well, remember the graph of it here. Actually, let's just look at the graph that we had right here. If it's to the right of negative 6, if x is positive, bigger than negative 6 I should say, well, the function is just x plus 6. So it's just equal to x plus 6 if x is greater than negative 6. But now if we get to the left, here we have a decreasing function. It's negative. The opposite of that if x is less than negative 6. We don't really care about if x is equal to negative 6 because we're taking a limit as x approaches negative 6. We only care about values that are close to negative 6. So remember the definition of an absolute value. It's the actual function itself if what comes out is going to be positive, but it's the opposite of that if what comes out is going to be negative. Well, so we actually have two types of functions then. Well, two limits that we need to look at. If we look at the function limit as x approaches negative 6 from the right, well, from the right, when x is bigger than negative 6, we're coming in on this line right here in our denominator function, which is just the line y equals x plus 6. So we have this. Now this is equal to the limit as x approaches negative 6 from the right of 2 times the quantity of x plus 6 divided by x plus 6. Notice that those divide to 1, and so we're left with then the limit as x approaches negative 6 from the right of 2, which by the constant rule is just equal to 2. But if we take the limit as x approaches negative 6 from the left, approaching it from the left, we're approaching it on the line negative the quantity of x plus 6, or negative x minus 6, if we distribute that through. So we are approaching it on a different line here. So we have, coming at this thing from the left, we have the negative quantity of x plus 6, which again then we can rewrite the numerator as 2 times the quantity of x plus 6 divided by negative the quantity of x plus 6. Here the x plus 6 is divided to 1 again, but this is then equal to the limit as x goes to 6 from the left of negative 2, which of course is just negative 2, 2 over negative 1. Well, since the limits don't agree, coming from the right and coming from the left for our function f of x, we came from the right, we got a positive 2, coming from the left we got a negative 2. That means that the limit overall of f of x as x approaches negative 6, there it should be negative 6's, does not exist. So that limit does not exist because it's different coming from the left and the right. And it's just because of the nature of the absolute value function. Depending on which way you're approaching it with two different lines. And so we got two different limits as we came in from the left and the right because of the function itself, 2x plus 12 over the absolute value of x plus 6. We were able to cancel things down. Positive 2 coming from the right, negative 2 coming from the left. They don't agree, so the overall limit does not exist. All right, you should be in good shape for your 2.3 homework. Let me know if you have any questions. Your password for 2.3 is vivacious, which of course just means lively, or lively in spirit. All right, so vivacious is your word for 2.3. Good luck with that. And again, let me know if you have questions.